Hello there ATS 114 students, Dr. John Schrage here. I hope you are getting off to a great start this semester at Creighton University, and I'm here to give you a little bit of an introduction on how to do this first little homemade lab activity that we have made for you in the class. We know that at this point in the semester often a lot of students are still waiting for their lab manuals to show up, and you haven't covered a lot of material yet in the lecture, and so it just makes sense for us to kind of do a little homemade activity that will help make sure that you're up to speed on some of your basic ideas about how air works and how to use your calculator when you're solving problems in the class and so on. And so the problem that we're going to be addressing today is basically about the nature of air in terms of what air molecules are doing. This is it's a little gap in how air tends to be explained to you in your, say, high school physics classes or like an earth science class or something like that. I mean, pretty much regardless of where you got your background in such things in high school or whatever, you probably already know that gases are made up of molecules that are zipping around and bumping into each other. Something like this little animation is showing. And that's all very true. That is in fact exactly what air is like, but generally when you are taught something like that, a few important details about that are omitted. For example, I mean, I see this little animation here, but it isn't really telling me how fast those molecules are moving. I mean, it's just sort of a little cheesy animation here. How fast are the air molecules in the room moving? It's going to turn out today that you're going to learn that, as you may know from like a high school science class, it is the temperature of an object, of a material, that determines how fast the molecules are moving. But there's actually more to it than that. It's also the molecular weight of the materials in question. Air, which is a mixture of different materials like nitrogen and oxygen and carbon dioxide and argon and so on, will have different molecular weights. The different materials have different molecular weights, and therefore if you have a sample of air like in this little box right here, and it's made up of lots of different kinds of molecules, all of those molecules are at the same temperature, but they'll be moving different speeds. The lighter molecules will be moving at one set of speeds, the heavier ones will be moving at another, as you'll be seeing in this activity. You probably hadn't pictured that way, that like some of these molecules are moving faster and some are moving slower. Another question that is typically not answered when you are learning about gases as being, made up of molecules that are in motion and bouncing against each other is how far do they move? How far apart are these collisions between individual molecules in a sample of air? In the atmospheric sciences, we have a term for that property. We call it the mean free path. And there's a fairly basic equation for determining the mean free path of air you're going to have in this activity. And it depends on things like the temperature of the air and the pressure of the air, and also the size of the molecules that are colliding with each other. Obviously, a bigger molecule is more likely to bump into each other than smaller molecules are, and so on. Notice I've now a couple times mentioned the word equations. Yes, you're going to be using equations. There will be equations in lots of the activities that we are doing in this lab course, and in general, most of the time that's not really a big problem for students. People know how to punch numbers into their calculator until they get sometimes a little spooked about scientific notation and how to use the exponential button on their calculator. I mean, if you see a number in an equation like this one here, 5.45 times 10 to the third, okay, one way to solve that is just to do the thing that you probably learned in like junior high about moving the decimal point. And that can be a good strategy. I do that all the time when I'm checking things too. And so, like for example, if I have a positive exponential here, 5.45 times 10 to the positive third, that means I move the decimal place 3 points to the right. So my resulting number is not it is 5.45 times 10 to the third, which is going to be the same thing as moving the decimal place 3 points to the right, which gives me 5,450. In the same sort of way, I could have a negative exponential there in my scientific notation. What would the number be if I got 5.54 times 10 to the negative third? Times 10 to the negative third with a negative exponential there means that we are going to be moving the decimal place 3 points to the left. So you might have to, add some zeros at the beginning of that to make this work, but you'll end up with, 0.00545 in this case, by moving the decimal place 3 points over to the right. That's all well and good, and you're certainly welcome to do that as much as you need to on any of the assignments here, but some of them are going to have really big numbers in the exponential there, like 5.45 times 10 to the negative 23rd. Well, feel free to write a whole string of zeros out there in front and then move your decimal place 23 points off to the left, but that's a very error-prone thing. Are you really sure you're going to count those all right or enter those all right into your calculator or whatever? seems very error-prone. A better strategy would be to work with it in the exponential notation. And odds are you have a calculator that can do that. You probably have a scientific calculator. And if you don't, you know what? Turned out mine had broken, I don't know if the battery's out or whatever, but you know where you can get one? Google. Google the words scientific calculator, and you'll get a scientific calculator. Okay, you can get any number of free scientific calculator apps for your phone, your iPad, I don't care. They're all going to have an EXP button on the calculator down here. And that's how you do scientific notations or exponentials. You're going to write, like for example, 5.45, and then press the EXP button. And then if needed, the negative buttons, because that, you know, like if you have a negative button here, negative exponential, so like 5.45 times 10 to the negative 23rd. Okay? A scientific calculator can work with that just fine. It can do with calculations with that. Here we'll do 5.45 times 10 to the negative 23rd, and we'll take that quantity times 5. Okay, and look, even the answer came back in exponential notation, in a scientific notation like this. It's going to be pretty straightforward. You know, it's one of those things where if you haven't done it in a long time, you might kind of forget how to make exponentials and scientific notation work on your calculator. If you have done it recently, it's so second nature you can't believe we actually reviewed that going into a lab. So today's lab activity, you're going to be kind of learning a little bit about the atmosphere as to why it is the way it is, and you're getting some experience, just because I know there's some problems coming where you're going to need to use scientific notation on your calculator. What you're going to learn today, you're going to see that the molecules in the air at room temperature are moving really fast. Okay, it's going to be way faster than like 1,000 miles per hour. Our air molecules are really moving very, very fast. You're also going to find that at the temperatures and pressures we observe down here at the surface of the Earth, the mean free path is not very long at all. I'll leave it to you to see how short it is, but it is very, very short. I'm always amazed by that. You know, what could look more tranquil than a sample of air? But air is this giant, violent collision factory. Okay, this sample of air is... These air molecules are moving at greater than 1,000 miles per hour, and they're colliding with other molecules literally like trillions of times per second. It's not what you're expecting at all when you think about what air should be like. So in general, in the atmosphere, the molecules don't move very far at any given between collisions, and they're moving really fast. There's only one big exception to that, and that's really high up in the atmosphere. We're talking more than 500 kilometers up. At those altitudes, the mean free path in the atmosphere gets very long. Because the molecules are so far apart, molecules can travel kilometers, even more, without hitting each other. And the temperatures up there in that part of the atmosphere, called the thermosphere, get very, very high. So you have very high temperatures with molecules going very fast, and they're very far apart. They're almost never colliding with each other. In fact, some of these molecules will have such great speeds and be going so far before they have a chance to hit another molecule that they'll actually be going faster than the escape velocity of the Earth. The speed at which, you know, like a rocket or whatever, any kind of ballistic projectile needs in order to escape the gravity of the Earth. Some of the air molecules literally head off into interplanetary space. The gases of those molecules will just be gone. We're losing them off to space. Which is why when you see a diagram that shows you the a list of the constituents of the Earth's atmosphere, and I know in one of the sections of the lecture you're going to have seen basically this exact diagram here, you can see that the Earth's atmosphere is made of certain kinds of molecules like nitrogen and oxygen and carbon dioxide, and not made of some things you might have thought would be in the atmosphere like helium and hydrogen. Okay? Well, now we're learning why. We're going to do the math today to find out, but you're going to find out that these gases are moving, their molecules are moving so fast that at least above, once they're up there in the thermosphere, those molecules tend to just bleed off into interplanetary space, and we don't even maintain that part. We only keep these heavier, slower moving molecules in our atmosphere. That's going to lead you to think you've got it all figured out as to why there's no atmosphere on the moon. I mean, the moon is much lighter than the Earth. The moon has a much weaker force of gravity, a much lower escape velocity, and you're going to find out, hey, wait a minute. At the moon, almost any air molecule has a fast enough motion to have the escape velocity of the moon. I get it. The molecules are just bleeding off. You can't have an atmosphere on the moon. And maybe yes and maybe no, because then in the last problem I'm going to steer you towards Titan, a moon of Saturn that happens to be a little bit smaller than Earth's moon. It has an even slightly weaker force of gravity and even slightly smaller escape velocity. So it seems like molecules should be able to just move fast and escape the gravitational field of Titan. Titan has an atmosphere. How does it manage to do that? You're going to have to think through about what are the speeds of these molecules and what does their mean free path and so on. You'll be able to figure out why does Titan have an atmosphere but the Moon doesn't. Alright, we're kind of looking over a whole bunch of very basic ideas about the nature of air in this little lab activity. Probably won't take you very long. You might need your TA to help you a little bit with how to get your calculator or whatever calculator app or whatever you're using working. Please let me know if you have any questions or talk to your TAs, and I hope you have a great lab activity, and we'll see you next week.